California, and you can see Talis birdies right there sticking out. This is same spot. Same spot. What is going on, guys? I'm showing you what? We're getting what? Closer. All right, good job. All right, good for you. We're getting closer. Woo-hoo. We're getting closer. And we are getting closer. So this is not accurate. Just play with me, okay? So let's just say, okay, at this scale, it's looking at reality with your eyes. And this scale is looking at reality through a microscope. Here's looking at electron microscopy, really close. And here is looking at the subatomic level. Notice something suddenly changed, yes? At this level, the natural laws we experience through everyday experience breaks down or no longer apply. Completely different set of rules apply here. Now, Steve Hawking, one of the best-known physicists of our time, said in one of his books that electromagnetic forces are responsible for all chemistry and biology. All chemistry and biology describes everything around us. Yes? In other words, you understand the electromagnetic force, you understand your environment. Yeah? Now, when you combine relativity, elements of relativity we sort of quickly looked at, and you combine that with quantum mechanics, which is our rules of the subatomic world, you get a quantum field theory. The quantum field theory that describes electromagnetic radiation is quantum electrodynamics, QED. So we're all familiar, we've all seen this before, yes? This is spectrum of electromagnetic radiation. We can see with our eyes a very small piece of it. Here's another representation of the same thing. Here you can see that the wavelength is different right across the spectrum. So again, we can see a very small chunk of it. We can hear this part of it along the wavelength. Using machines, we can actually hear it. We can cook our hot dogs over here. We can see our bones here. And here we can cook ourselves with it. Now QED can predict what happens in chemistry. So one way of evaluating sort of scientific theories, how well does it predict nature? Now here we have two hydrogen molecules and an oxygen molecule. They come together and they make each other very happy by sharing electrons. So we know that the mass of an atom is in its nucleus, yes? Right? So the electron doesn't really have any mass at all, right? It's really just like energy, yeah? So I want you to really think about this really carefully. So an oxygen comes around with two hydrogen and they share the electron. So that change two gases at room temperature into a liquid at room temperature, which is the foundation of all life on Earth. I want you to sit with that. A very small shift. And with just these two elements coming together, sharing an electron, changes gas into life-supporting water. And this is predicted, understood with QED. Here's another element. This is chlorine. So what you're seeing is this is the nucleus, and these are dots represent electrons. Chlorine is a noxious gas. You would not want to meet chlorine as a gas. You die a very unpleasant death very quickly. And here we have sodium. So these guys come together. You notice there's one electron hanging out there feeling kind of lonely. So, and there's one little spot there for an electron. So this electron just goes over there, and that makes them really happy and clung onto each other. And that you put on the spaghetti. Now, this is the only thing that's happened. One little electron moved from here to over there, but turned into a toxic gas into food. Very, very small energetic shift. I love rocks. So you're looking at rocks at plain light, and here you're looking at rocks at light at different wavelengths. These are glowing rocks. Rocks glow. Isn't that awesome? More glowing rocks. More glowing rocks. I love glowing rocks. Now, how do rocks glow? Well, community explains that too. Well, sort of like, okay, so you've got energy, electromagnetic radiation. All electromagnetic radiation is carried by a photon. Right? So photon brings this energy, hits the rock, and sort of gives it energy, and then one of the electrons gets this all energized, jumps up to the higher level, and then it jumps back to its ordinary level. In that process, it gives out a photon of light. That's how the rocks glow. And this is sort of, what somebody's imagination, what a photon might look like. It has no mass. And here again, it's not, I will talk without this understanding. We will not have transistors. Can you imagine life without transistors? There will be no fiber optics, no laser, and oh my God, no World Wide Web. How can we live? And certainly, that's what makes our lifestyle possible, yeah? Okay, wrong button. Okay, so that's quantum mechanics combined with relativity, quantum field theory. So what kind of sort of picture does it paint about nature? Well, here's a really famous experiment called the double slit experiment. What scientists have been doing and still doing it, they keep trying with different things. They try electrons, and recently they started with buckyball atoms, like we're trying to do bigger and bigger things. People are now trying to throw virus through it and see what happens. So what they're doing is they shoot an electron, one electron at a time. Now here where I'm showing you interference patterns. So you have a wave, you have two waves travel side by side where the crest lines up with the crest and trough lines up with the trough like this. The energy adds up, they become a bigger wave. Right? They add up together. And if they're offset, the crest with trough with crest, then they cancel each other out. Right? They create, so either stronger, like here it is, what you're seeing, stronger or weaker, canceled out, none. Right? So what you're looking at here is an interference pattern. And interference patterns are produced by waves. So if we shoot an electron as a particle, as a thing across this double slit, in the end you get an interference pattern. That tells us it is behaving as a particle and as a wave. Not only that, because we're shooting at one at a time, and we see interference pattern, that means the electron has to be passing through both of these slits at the same time and come out and interfere with itself. And recently, we started even messing with it even more. And all the other reasons, let me backtrack. So what happens then is, wait a minute, how does this happen? Let's spy on the electrons. Let's put sort of some kind of observation device here and see where the electron is going. And how does it get through? Which slit is going through? The minute you put measuring device here, this pattern goes away. So instead of going both slits at one time, because you're spying on it, it just goes where you want it to go. It's going through the slit you're measuring at it. One at a time. Then we are messing with it again, right? I say, okay, we're going to try to trick the electrons. We're not going to decide if we're going to measure until the electron is just about to hit the screen. So we're going to wait till it's just about to hit, and it's going to just push the button. And guess what? The electron still does the same thing. If you measure, interference pattern goes away. If you don't measure, you see the interference pattern. Time is traveling backwards. This is all experimentally shown. This is not just I didn't see anything weird just now. So if you're curious, go online. There's all kinds of videos explaining the double slit experiment. It's really fascinating. So what we've learned from all this is that everything, all radiation and matter can be either particle or wave. In fact, it's neither. It's a particle, you want to measure it as a particle, it's a wave, you will look for it as a wave. And obviously, as we've said, the act of observation changes it. So the observation effect. When you observe something, you actually change it. And more recently, we got more like trickier and trickier all the time. Let's put a measuring device that has a very, very weak length on it and see what happens. Well, actually, because it's so weak, so some percent of it interferes and some doesn't, depending on the strength of the observation. Tricky, huh? So you cannot observe a system without changing it. Oh, what is this? Who cares about all this? Well, remember, this is what makes our lifestyle possible. In addition, all the machines will be making, some people have said, if we could be more energy efficient, we would not need any more energy. So man-made systems are not very efficient at all. So everybody knows electricity is the movement of electrons through wires, yes? Right? So and the wire is resistant. I don't want you to get through me. Right? You write all this resistance and they use up all this energy, produces heat, right? But natural system doesn't do that. So natural systems have efficiency of over 95%. It's like, how do they do that? Right? We're trying to figure out how that works. So recently, a couple of groups of researchers, one group in Berkeley and one group I forgot where, have been able to show that the reason nature can be so efficient is that electrons would explore all possibilities, all possible pathways simultaneously and collapses into the most efficient way. So this is how nature works. The weird quantum world that we can't, it's like a is actually how nature works. And we all know photosynthesis is the basis of life for us, yeah? Without photosynthesis, without life, yes? So, if we really get this, so what kind of shift can we make from this? Well, we can shift from the idea that reality is fixed as how we see it, or reality is observer dependent. Outcome is observer dependent. So you can look at this and say, oh my God, my world is falling apart. The only thing I knew that's a part of me all this life is crumbling. Or you can say, oh my God, this breakdown is necessary because it's keeping me from the next way of life. We can move from resistance to welcoming currently unimaginable possibilities. Man-made systems are full of resistance. Nature is not. It is resistance that causes suffering. And it's completely unnecessary. So in that context, the phrase is, well, it takes time to breathe and change. Makes no sense. That is only sort of one possible reality. If we really know how nature really works, that makes no sense at all. None whatsoever. So actually, I'm going to put a pause button right now because I think you're sick of listening to me. For right now, no. I just want to take a couple of minutes for you to say one thing that you've gotten so far. We will have a discussion at the end when I'm done with all this stuff, and I really like to have a conversation with everyone. But right now, I want you to just talk to your neighbor and share with each other one thing that you are sort of thinking about right